Okay, we're now going to look at example 2 again. This is another situation where a quantity is increasing or decreasing over a period of time t, and we're not given the index equation which models it. So we need to get the index equation. So it says a radioactive substance loses its mass at a rate of 5% per century. And then it goes on to say, find in years its half-life. In other words, find the time taken for its initial mass to be halved. Now, frankly, the second sentence is totally irrelevant until we write down the equation and get the specific equation, index equation, that represents this situation. So, the first thing is the quantity, in other words, the mass of the substance, is it increasing or decreasing over time? It's clearly decreasing because it loses its mass at a rate of 5% per century. So what I'm going to do is write down the basic index equation for decay, but I'm going to use m instead of y because m represents mass. So I'm going to let m, so that's the mass at any time t, equal m0. That's the initial mass of the substance at time t is 0. And that's multiplied by A. Remember, A is a base, any positive base except 1. And the power of A is going to be negative kT. It's negative because the mass, the quantity, is decreasing over time. And remember, K is a constant and T is obviously the time. Now, we can't really use this equation until we work out quite a few of the unknowns. Remember, m0, a, and k, they're always constant, so if possible, let's try and work them out and always start with the base a. It's always the trickiest one to work out. So let's get the base a. Remember, the base A is the multiplying value which describes the percentage increase or decrease. In this case, it's a percentage decrease. So in order to do that, we're going to consider how the mass changes per unit time. And the unit time here is per century. So how is the mass M changing per century? Okay, so how the mass changes per the first century. So again, put start down, and then that's the start of this first century, and then finish, end of that first century. And again, what happens during that first century is the mass decreases by 5%. Now, at the start of the century, we don't know the mass of the substance other than its m0, that's the initial mass, so I'm just going to write down m0. Remember, in the last example there were 20 rabbits, but we're not told the initial mass, we're just going to keep it as m0, and that is worth 100%. If we decrease 100% by 5%, then we're going to be left with 95%. Now, there's two ways we can describe the decrease. We can either say what you start with, you decrease it by 5% to get what you finish with, or the other way you can describe it is, well, if you start with 100% and you multiply it by 0.95, that's going to give you 95%. So this multiplying value which describes the decrease is the base A. And while we're on this particular piece of working, we may as well work out the mass that we're left with at the end of the first century. So if you start with M0 and you multiply it by 0.95, you're going to finish with 0.95 M0. So we've worked out the base A. Yes, we don't know what M0 is, but we have worked out A. What we're going to try and do now is work out K. Always try to get the constant after you've worked out the base. So get K. Now, okay, so in order to get K, we're going to sub everything we know into our general index equation. So we know at the end of the century, the mass M that we're left with is 0.95 M0. Okay, so we're left with 0.95 M0. So we're going to sub in capital M. The mass is 0.95 M0. We're also going to sub in A. A is obviously 0.95. That's the base. Obviously K is what we're trying to find. Now we need to be careful. Here's a potential area for a mistake. The time is the first century. Now we're not going to sub in T as 1 because if you go back to the example it says find in years the half-life. So we want the time to be in years. So I'm going to sub in not T as 1, I'm going to sub in T as 100 because 1 century is 100 years. We want to work in years. So hopefully we'll sub all this information in and fingers crossed we're going to work out what the constant K is. So let's chuck it all in. So we're going to get M is 0.95 M0 and that's equal to M0 and then that's multiplied by 0.95 in brackets, that's our base A. And then it's to the power of minus K and then multiplied by 100. Okay, so looks positive. We're not liking the M0s because we only want there to be one unknown, but that's fine. We can divide both sides by M0. So let's do that. So we're going to end up with 0.95 is equal to 0.95. And that's to the power of minus 100k. Now, we now have an index equation and we want to solve it to get k. But again, there's a smart way of doing this because look, the bases are already the same, so you don't need to take natural log of both sides. You can if you want, it's just more work. The bases are already the same, so all we do is equate the powers. So 1 must equal to minus 100k. And then we're going to divide both sides by minus 100, so we're going to get minus 1 over 100 is equal to k. And there we go. We've just worked out the constant. So that's super news. We've got the base, we've got the constant. So we're now going to go back and we're going to write down the index equation which models the decay of this radioactive substance. Okay, so go back. We have capital M, so that's the mass of the substance at any time t, and that's equal to M0, the initial mass at time t is 0, and then A is 0.95, and then to the minus, and then K is minus 1 over 100, and again put the constant in brackets once you've worked it out. And then that's being multiplied by t. T is the time and we're working here in years. So that's a pretty good equation. You could tidy these two minuses up and you could end up with a plus there. That's okay as well. So now we're in a position where we can answer the second part of the question. The second part of the question is find in years the half-life of the radioactive substance. In other words, the time taken for its initial mass to be halved. So what we're going to do is we're going to sub in half of its initial mass. So we're going to sub in m0 over 2, or a half m0, and then we're going to work out what t is in years. So at this stage we're going to sub in capital M, so the remaining mass being m0 over 2. So we're replacing the mass m with m0 over 2. The remaining mass is m0 over 2. Find t. So we're going to get m0 over 2, or a half m0, is equal to m0 upon 0.95, and that's to the power of negative, and then in brackets negative 1 over 100 multiplied by t. Now the beauty about it is, again, the m0's cancel out, so we're going to divide through by m0. So we're just going to end up with a half. And then on this side we're going to have 0.95. And again, what we could do is multiply these two minuses together, so that's going to give us a plus. So we're going to have 0.95 to the positive 1 over 100t. And again, I'm just going to keep brackets around that 1 over 100. Okay, that value, and then t outside. So what we have now again is an index equation. The unknown is part of the power. So we're going to take natural log of both sides. So natural log of a half, and that's equal to the natural log of 0.95, and that's to the power of 1 over 100t. So I'm now going to use log rule 3 here to make this power the coefficient of this log. So we're now going to get natural log of a half, and that's equal to 1 over 100 and then t times the natural log of 0.95. Okay, plan. I'm going to divide both sides by the natural log of 0.95. So we're going to get natural log of a half all over natural log of 0.95, and that's equal to 1 over 100 multiplied by t. Okay, now 1 over 100 multiplied by t is just t over 100. So what I'm going to do now is I'm going to multiply both sides by 100, and that will cancel this 100 down there. So multiply both sides by 100. So we're going to get 100 times the natural log of a half over the natural log of 0.95, and that's just going to equal t. So at this stage we can go to our calculator and then evaluate t, and remember t will now be in years. So go to our calculator. So we're typing in 100 times the natural log of a half, and then that's all over the natural log of 0.95. Okay, and then hit equals. So we're going to get 1351.3407. So t is therefore equal to 1351 0.3407. And then we'll give it to 3SF, so answer time is 1350 years, and that's the 3SF. So that is how many years it takes for half of the initial mass of the substance to decay, and therefore we're left with half of it.